Good afternoon, ladies and gentlemen. Can you all hear me? In the chat functionality, if you can just give me an indication. Awesome. So yesterday we finished off with the slide of what is cycles of the sun. So I thought I'm going to show you a small video to explain a bit more about cycles of the sun and the moon and a few other objects as well. Then we'll take it from there. This lecture recording will also be made available afterwards on YouTube. So let's start off with today's lecture.
Under a dark sky, you can see thousands of stars. If you watch for a few hours, you can see them rise and set as the Earth rotates once a day. And if you go outside the next night at the same time, you'll see that things look pretty much the same as they did the night before. The stars rise and set, Polaris hangs to the north, and so on. One day hardly makes any difference to the sky's appearance. But what if you wait for another night or a week? If you're that patient and observant, you can spot subtle changes in the sky. Let's say a couple of weeks have passed. Remember that star that was just over a tree in the east when the sun set? The one that made you first notice the stars are rising and setting? Go look at it again. If you happen to be out at the same time, you'd expect that star to be in the same place. But it's not. It's actually a bit higher above the tree. And if you look west, stars that were well off the horizon just after sunset last week are now lower. If you wait a month, this effect is even more pronounced. All new constellations will be visible in the sky after sunset. This is because the Earth is going around the sun, literally changing our viewpoint on the sky. The Earth takes a year to orbit the sun once. Every day, it moves a little bit along its orbit. And as it does, from Earth's perspective, distant stars appear to move their positions relative to the sun. So one day we might see a star very near the sun, but the next day the angle is a bit bigger. At some point, about 6 months after we first saw it, the star is directly opposite the sun in the sky. Then the angle starts to shrink again as the star approaches the sun from the opposite side until, after a full year, the cycle repeats. What this means to you, the naked eye observer, is that the stars appear to rise and set at different times over the course of the year. Stars in the east rise about 4 minutes earlier every night, and stars in the west set 4 minutes earlier. A constellation that was entirely below the eastern horizon at sunset one month might be completely visible after sunset the next month. Another way to think about it is that the stars appear to be fixed, and as the Earth circles the sun moves through the stars over the course of the year, making a complete circle around the sky once per year. The path it takes is a reflection of the Earth's path around the sun, a line in the sky. That means the sun passes through the same constellations in the sky every year. We give those constellations a special name, the zodiac. Every year during a given month, the sun will appear to be in a certain zodiacal constellation, from Sagittarius through Scorpius, Libra, Virgo, Leo, Cancer, and the rest. Eventually, over a year, the sun returns to Sagittarius and the cycle starts again. But even though we talk about this process in terms of the sun's movement, it's really the path traveled by the Earth that creates this effect, as our perspective moves with it. And of course, the planets move in the sky as well. Mercury, Venus, Mars, they orbit the sun too, and they do so in approximately the same plane the Earth does. If you could see the solar system from the side, it would look flat. So to us on Earth, the planets go around the sky over the course of a year, and they also appear to change their positions relative to the sun and the stars. The inner planets, Mercury and Venus, move so rapidly you can see their motion after a single night. The outer planets are more leisurely, but wait long enough and they too will be seen to move, sliding through the constellations. By the way, the word planet is Greek for wanderer. There's another aspect of all this you might notice over time. You've probably seen a globe and noticed that the axis of it is tilted. That is, it's not straight up and down, perpendicular to how it sits. That's because a globe is modeling the Earth, and the Earth is tilted. The Earth spins on its axis once per day and orbits the sun once per year. But the Earth's axis is tilted with respect to its orbital plane by 23.5 degrees. And this has a profound effect on our planet. Imagine for a moment that the Earth's axis were exactly perpendicular to its orbit, straight up and down. If that were the case, every day, the sun would take the same path across the sky. If you were on the equator, the sun would rise, go exactly overhead, and then set. If you're on the pole, the sun would appear to go around the horizon every day, neither rising nor setting. It would always be twilight. But that's not the case. The Earth is tilted. In the months of June and July, the Earth's north pole is tipped toward the sun. 6 months later, it's pointed away. This affects the path the sun takes across the sky. Instead of it taking the same path every day, in the northern summer, when we're tipped toward the sun takes a higher path in the sky. Because that path is longer, the days are longer too. 6 months later, in December and January, the Earth's pole is tipped away. The sun takes a lower path in the sky, and because the path is shorter, days are shorter too. That's why we have seasons. When the sun is up high in the sky, it shines straight down on the ground, heating it better. And days are longer, so it has more time to heat us up. It gets hot. In the winter, it's the reverse. The sun is lower, so it can't warm us up as efficiently, and it has less time to do so. It gets cold. There you go. Seasons. The Earth's axis is tipped. If it weren't, the seasons wouldn't occur, and the temperature of the Earth wouldn't change month to month. There's a common misconception that the Earth has seasons because it orbits the sun on an ellipse, and so it's closer to the sun in summer and farther in winter. While it's true the orbit is elliptical, Earth is closer to the sun in January, on the order of 5 million kilometers or so, than it is in July. It's the angle of the sun's rays that makes winter cold and summer hot, not our distance from the sun. Also, you may know that when it's summer in the northern hemisphere, it's winter in the southern. When the North Pole is tipped toward the sun, the South Pole is tipped away. So northern and southern hemisphere seasons are opposite each other. But nothing in astronomy is permanent. The North Pole's not always going to point toward the sun in June, and Polaris is not always going to be the North Star. That's because our planet's axis is actually moving. Have you ever seen a spinning top start to wobble, its axis moving in a slow circle even as the top itself spins? This is called precession, and the Earth does it too. Our planet spins on its axis once per day, but the axis wobbles, making a very slow circle that takes 26,000 years to complete. This affects a lot of what we see in the sky. For example, Polaris won't always be the pole star. Every year, the pole points a little farther from that star, making a big circle 47 degrees across. For ancient Egyptians, the star Thuban was the pole star, and in about 11,000 years, that position will be held by the bright star Vega. Also, the date the sun is in a particular zodiac constellation changes slowly due to precession as well. When the ancients first thought up this idea, the sun was in Aries on March 22nd. The vernal equinox, what some people call the first day of spring. But due to precession, it's now in Pisces. That's why your astrological sign doesn't match where the sun actually is in the sky. 2,000 years of precession has changed them. One of the many reasons astrology is silly. It's incredible to think about. The Earth, the sun, the stars. They allow us to tell the time and time of year just by looking up and paying attention. This is why the stars were so important to ancient humans. The stars were like a clock and a calendar in the sky, long before we had invented either. We've actually learned a lot about the sky just by looking at it. Of course, some of the stuff I've explained we've learned through other means. The Earth is spinning. Stars have different intrinsic brightnesses, and so on. But all of that knowledge, and far more, got its start by people who went outside and looked up. Later, as we applied math and physics to what we observed, we learned even more, and could then go back and explain what we saw. So don't discount naked eye astronomy. It's all we had for thousands of years. In fact, I think we lost something when we started using clocks and calendars and moving to cities with bright lights that washed away the stars from the sky. Those folks long ago were tied to the sky. They knew it like you know the streets in your neighborhood. They could see the stars rise and set. They knew the glory of the Milky Way sprawled across the heavens, even if they didn't know exactly what it was. We do know now with our knowledge gained over the centuries, but it comes at the cost of losing touch with the sky, not living under it as much as we once did. I've spent thousands of hours over my life at night just simply looking up, watching the stars, appreciating the universe as I can see it. The things I have witnessed have shaped my life and instilled in me a permanent and endless sense of wonder and joy. The universe belongs to everyone. Go outside, and if you can, soak up your share. Today we talked about cycles. As the Earth goes around the sun, we see stars rise
So that is actually quite cool, and that explains clearly, or in a better way, let me see if I can get a pointer out, of how the zodiac works and how everything in the night sky is continuously changing. So when we look at this, it's not Earth, but the sun also goes through a annual motion. So let me just move the annotations. So when we look at the notion of the sky, for the zodiac, so for the Earth to complete a rotation and need to keep track where the zodiac is, that roughly takes 365.26 days. And that is 360 days around the ecliptic. So that means in roughly 24 hours, the sun moves 1 degree eastward, which is actually quite interesting. And then from this, it's also important to note that our seasons is due to the Earth's cant of roughly 23.4 degrees. Nothing to do with the distance from Earth. It has everything to do with the tilt of Earth's axis. So when we look at the axis of this 23.4 degrees, we can see vernal equinox in Northern Hemisphere is on 20 March, summer solstice is 22 June, autumn equinox is 22 December, and winter solstice is 21 December. So in the Southern Hemisphere, it's just the opposite around. So in South Africa, the summer solstice is on 21st of December. The spring equinox is the 22nd of September. Winter solstice is the 22nd of June. And the vernal equinox is the 20th of March. So this is quite important. So throughout the years while teaching this course, I have stumbled onto some really, really weird answers when I ask. This is a question or a hint for you guys that I like to ask in the semester test and the exam, is what causes different seasons on Earth. So it's nothing to do with the distance from the Earth to the sun, but this tilt of the axis of 23.4 degrees. So let me get a marker out. So when we look at this, how it is tilted, we can see now the northern hemisphere. So let's divide this into, this is the equator. So we can see the northern hemisphere receives more direct sunlight. So here we can see the path to the sun is direct. And in the summer hemisphere, let's get out of color. In the southern hemisphere, this is not direct. So due to this area being at an angle, we receive less direct sunlight. So therefore, in the northern hemisphere, it will now be summer. And in the southern hemisphere, it will now be winter. Does everyone understand that? Or would you like me to explain it in a different way?
Please explain a different way.
Sorry?
Please explain in a different way.
Okay, so let me explain it. So let's go back to the next slide. Now it's the other way around. So we have now, and the southern hemisphere will now have summer, and the northern hemisphere will now have winter. So as we can see from this image, let me get this out. So here is the imaginary line of axis. We can see the angle that this makes. So this angle over here between this spot and this spot is 23.4 degrees. So let me clear this annotations again. So now what that means is if we purely look at the line of axis, the southern part now receives less direct sunlight, northern part, and the southern part receives more direct sunlight, meaning you have more direct sunlight. If you have more direct sunlight, it means the days is longer, and you receive more energy from the sun, and that is why it's summer. If you are tilted away, such as in the northern hemisphere right now, you get less direct sunlight, meaning you have less energy from the sun, and therefore it is colder in winter. So in summer, days are also longer than in winter. So when we go back a slide, this is now just the opposite direction.
Right.
It is summer in the northern hemisphere because the northern hemisphere receives more sunlight and longer sunlight because days are longer, and therefore it is warmer than the southern hemisphere. Does that answer the question?
Okay.
Okay,
Yes, sir.
awesome.
Right.
So with that, we also get motions of planets. So the closer you are to the sun, usually we look at Kepler's laws of motion, the planets moves, so Mercury and Venus will orbit the sun faster than the outer planets. For example, our own sun takes 1 year to orbit around the sun. But if we take the sun, the Saturn, for example, it takes nearly 30 years to orbit once around the sun. So therefore, planets comes from the Greek word meaning wanderer, because they move around in the night sky. So by tradition, you guys have also heard probably about the evening star and the morning star. So that will be a bright star when the sun is setting and when the sun is rising. And the morning star is a misconception. It's not really a star, but it is a planet, and that planet is Venus. So depending on which time of the year it is, Venus will be the morning star and will sometimes be the evening star. So right now, currently, just before sunset, if you look at the west, is actually Venus. And Venus is now currently at its brightest, it will be for this year. So it's actually very, very cool to observe. So centuries ago, astrology was an important part of astronomy. But these two fields has developed to complete and utter opposites. So yes, so the stars don't read, so it doesn't matter. So the stars is out. Doesn't matter about weather. So unfortunately, we can't see stars fall through clouds. But yes, behind the clouds, the star will be there. So when it clears up, so after this week, there's rain predicted for this entire week, you will still be able to see Venus in the late afternoons when the sun is setting into the early evening. And it's not as bright as it will be this year. So last time I checked, Venus brightness is currently sitting at round about minus 4.3 magnitude, which is quite good for this time of year. So as we already learned, and we start to realize that astrology and astronomy has split in the last 50 years or so. So astrology is now more of a superstition and based on what they can do. And as we can see in the videos from 2,000 years ago until now, the zodiac has actually changed. So I don't know how they predict what the future will do because absolute rubbish. So that's why I joke with astrology, and it absolutely means nothing. But astronomy is the science of what's happening in space. So now you guys also know where the zodiac comes from. So the zodiac are these 12 constellations around the ecliptic. And depending where we are looking at, or we say the sun is moving in that constellation, as I said in yesterday's class. So in June, when we are on Earth's orbit and we look towards the sun, then the sun seems like it's in Gemini. 6 months later, when we are over here and we look, then it's in Virgo. So 6 months, sorry, not 6 months, 3 months. Another 3 months passed. If you look back, then it is in Capricorn. So usually when we know December, beginning of January is Capricorns, because if you look at Earth and you look back in this direction, we see Capricorn, and the other way around. So that's just how the zodiac works. So these movements of the sun around the Earth around the sun, the different planets around the sun around the Milky Way galaxy also influence climate. So the seasons are produced by the annual. So what causes the change in zodiac? So the change in zodiac, as I said, let's get my pen out. If Earth is now here, and we look towards the sun, then whatever constellation behind it is the zodiac sign we are currently in. So 3 months later, Earth will be over here. So you look towards the sun. Now Virgo is behind the sun. So now we are in the Virgo zodiac. 3 months later, we're looking to the sun. Now we are in Capricorn. Does that answer your question? Awesome. So the seasons are produced by the annual motion of Earth around the sun, but subtle changes in the motion can have dramatic effects on climate. You don't notice these changes during your lifetime, but over thousands of years, they can bury continents under glaciers. So Earth is warmer, and there are no ice sheets even at the poles. So scientists have found evidence of at least 4 ice ages in Earth's past. And one occurred 2.5 billion years ago. But the other 3 that have been identified all occurred in the last billion years, so a much shorter time interval. So now we can put together and we can start setting up a hypothesis. So sometimes a theory or hypothesis is proposed long before scientists can find the critical evidence to test it. And that happened in the year 1920, when engineer and meteorologist Milutin Milankovitch proposed what became as the Milankovitch hypothesis. And that is that small changes in Earth's orbit, the precession and inclination, affects Earth's climate and cause an ice age. So by the middle 1970s, Earth scientists were able to collect the data that Milankovitch had lacked. So oceanographers dropped deep into the seafloor to collect long cores of sediment. In the laboratory, geologists could take samples from different depths of core and determine the age of the samples and the temperature of the oceans when they were deposited onto the seafloor. From this, scientists constructed a history of ocean temperatures that convincingly matched the predictions of the Milankovitch hypothesis. So the evidence seemed very strong, and by the 1980s, the Milankovitch hypothesis was widely considered the leading hypothesis to explain climate cycles during the current ice age. But science follows mostly an unstated set of rules that holds that the hypothesis must be tested over and over against all available evidence. And in 1988, scientists discovered an apparent contradiction in evidence. So in this image, in image A, we can see calculations based on a Milankovitch effect can predict the temperatures over time. And a warming illustrated by this globe shows here that took place from 25,000 to 10,000 years ago and ended in the last glaciation. In image B, we can see over the last 400,000 years, changes in ocean temperatures measured from fossils found in sediment layers from the seabed match changes in solar heating predicted by the Milankovitch effect. So with the Milankovitch hypothesis, it sees that the Earth goes through changes where it becomes a little bit hotter and then cooler, a little bit hotter and then cooler. But one thing that's stand out from the evidence is due to our pollution in the atmosphere, due to global warming, the Milankovitch cycles is the period is shortened, and also on average temperatures are rising. Yes, we have our periods, we still go through this a little bit warmer, a little bit cooler, but on average everything is rising. But we will do a in-depth lecture on that as well. So the next thing is our changeable moon, and after the semester you guys will know a lot about the moon. So before we continue, I want to show you another video.
Besides the sun, the moon is the most obvious object in the sky. Bright, silvery, with tantalizing features on its face, it's been the target of imagination, poetry, science, and even the occasional rocket. If you pay even the most cursory attention to it, you'll see that it changes every day. Sometimes it's up in the day, sometimes at night, and its shape is always changing. What causes this behavior? The moon is basically a giant ball of rock 3,500 kilometers across, hanging in space. Its surface is actually pretty dark, with about the same reflectivity as a chalkboard or asphalt. However, it looks bright to us because it's sitting in full sunlight. The sun illuminates it, and it reflects that light down to us here on Earth. And because it's a sphere and orbiting the Earth, the way we see it lit by the sun changes with time. That's what causes its phases. Geometry. The important thing to remember through all of this is because the moon is a ball and in space, half of it is always illuminated by the sun. This is true for the Earth too, and every spherical object in space. Half faces the sun, half faces away. We call the part facing the sun the daylight or bright side, and the half facing away the night or dark side. The phase of the moon refers to what shape the moon appears to us, how much of it we see illuminated from the Earth. The key to all this is this line, dividing the lit day side from the unlit night side. We call that line the terminator. If you're facing the moon with the sun behind you, you're seeing the half of the moon that is fully illuminated by sunlight, and it looks full. If you're off to the side, you see half of the lit side and half of the dark side, and we say the moon is half full. If the sun is on the other side of the moon, you're looking at the unlit half, and it looks dark. Now, mind you, I haven't moved anything except our point of view here. So at all times, the moon is always half lit and half dark. Remember that. The phase of the moon we see depends on from what direction the sunlight's hitting it, and the angle we see that from Earth. The moon orbits the Earth roughly once per month. In fact, that's where the word month comes from. Month and moon are cognates, words that have similar etymological histories. And in most languages, including English, the two words are very similar. The length of time we call the month is derived from the length of time it takes the moon to go through all of its phases, 29.5 days. So, to describe the phases, let's start at the beginning. New moon. New moon happens when the sun, moon, and Earth are all more or less in a line. The moon's orbit is actually tipped a bit to the Earth's, so sometimes the new moon happens when the moon is below the sun or above it. But at some point in its orbit, at some point in the month, it appears to be as close to the sun as it can. What does this look like from the Earth? The moon is between the Earth and the sun. So from our perspective, we only see the dark half, the unilluminated half of the moon. The other side, the far side of the moon, is lit, but we can't see it. It makes sense then to call this the beginning of the moon's cycle, hence the term new moon. Now think about this for a sec. Because the moon is near the sun in the sky, it travels across the sky with the sun. It's up during the day. You can only see it from the part of the Earth that's lit, which is when it's daytime. It's a very common misconception that the moon is only up at night, but it's up during the day literally just as often. At new moon, the moon stays near the sun, so it rises at sunrise and sets at sunset. This makes it extremely difficult to see. It is, after all, sitting next to the brightest object in the sky, and only a little bit of it is lit from our perspective. But not for long. Because the moon is orbiting the Earth, after a couple of days, it's moved a bit to the east. Now we're seeing it along a slight angle, and we can see a little bit of the illuminated half of the moon on its side toward the sun. The terminator, the day-night line, appears curved around the moon, so what we see is a thin, illuminated crescent moon. At this point, the crescent is still very thin, with the horns of the crescent pointing away from the sun. Note that the moon is still pretty close to the sun in the sky, just a bit to the east, rising maybe an hour or two after sunrise. But this means it's up all day and then sets after the sun does. This is the best time to see the crescent moon, when the sun is already set and the sky starts to get dark. The moon will be low over the western horizon, and it'll set soon after the sun does. Let's wait a couple of days. Okay, now the moon has moved a bit more in its orbit around the Earth, and is farther from the sun in the sky. We see a little more of the illuminated part, and the crescent is wider. Since it's getting thicker, we say this is a waxing crescent moon. Waxing means growing or getting bigger. It's also well away from the sun now, so it's easier to spot even during the day before sunset. 7 or so days after new moon, we get to our first milestone. The moon is now 1/4 of the way around its orbit. It's 90 degrees away from the sun in the sky, which means we're looking straight down on the terminator, the moon's day-night line. It cuts right down the middle of the visible face of the moon, so it's half lit, with the sunward side of the moon visible and the other side dark. Confusingly, this phase is properly named first quarter because the moon is 1/4 of the way through its cycle, 1/4 of the way through its orbit around the Earth, even though it looks half full. So it's not really the half full moon. Astronomers prefer first quarter. So if you want to sound all astronomery, then you should call it that. But time marches on. The moon continues on its gravitational dance with Earth, swinging around its orbit. Now more than half full, we say its shape is gibbous, which means swollen or convex. Here, this is actually the waxing gibbous phase of the moon. It rises in the late afternoon and is up most of the night. Our next big step comes 2 weeks after new moon, when it's moved halfway through its orbit. It's now opposite the sun in the sky, 180 degrees around. The Earth is between the moon and sun, so we're looking at the fully illuminated half of the moon. This is the full moon. Because it's opposite the sun, it rises at sunset and sets at sunrise. It's up all night shining down on Earth. But again, wait a couple of days and things change. When the moon is full, it's 180 degrees around the sky from the sun. So as it continues to move around the Earth in a circle, the distance between it and the sun is now starting to decrease, even if it continues on in the same direction. As before, it keeps rising and setting later, but now it rises after sunset and sets after sunrise. If you get up early in the morning as the sun is just rising in the east, you'll see the nearly but not quite full moon setting in the west. Not only that, but we're about to go through all the phases again, but in reverse order. A few days after full moon, the lit side is shrinking. It's in the waning or shrinking gibbous phase. Then, 3 weeks or so after new moon and a week after full, the moon is once again half lit, the terminator splitting the moon's face in 2 even halves. This is the third quarter moon because the moon is 3/4 of the way through its cycle. It's a lot like first quarter, but the side that was lit is now dark and vice versa. It's 270 degrees around the sky from the sun. It rises at midnight and sets at noon. A few days later, and the moon is a crescent again, getting thinner. It's now a waning crescent. It rises just a couple of hours before sunrise and sets a couple of hours before sunset. Then finally, we're back where we started. 1 month after new moon, the moon has traveled 360 degrees around the sky and is once again as close to the sun as it can get. It's new moon and the cycle starts up again as it has for time immemorial. An interesting thing happens if you move your perspective from the Earth to the moon. The phases of the moon we see from Earth depend on the angle of the moon and the sun in the sky. But on the moon, the angles are exactly 180 degrees reversed. At new moon, when the moon is between the Earth and sun, the Earth is opposite the sun as seen from the moon. It's full Earth. All the other phases are opposite too. So when we see a full moon, a moon dweller would see a new Earth, and so on. Have you ever looked at the thin crescent moon and seen the ghostly face of the rest of the unlit side? That's because it's not really unlit. The nearly full Earth is reflecting sunlight on the moon, lighting up the otherwise dark part. The Earth is bigger and more reflective than the moon, so it's actually 50 times brighter than a full moon. This glow is called Earthshine, a term I quite like. Even more poetically, it's been called the old moon in the new moon's arms, referring to the unlit part surrounded by the crescent new moon's horns. That's lovely, isn't it? The moon is one of the most beautiful and most gratifying objects in the sky to observe. It's different every day, yet it's also the same because we see more or less the same half of it, the same face all the time. It's big and bright, and the features on its surface discernible by eye, and even better with binoculars or a small telescope. As the phases change inexorably, day after day, the angle of sunlight hitting the surface changes, bringing new things into our view. The motions become comforting, even familiar. It's a reminder that the universe may seem strange and complicated and forbidding at first, but over time, as you get outside and experience it, it becomes your neighborhood. Welcome home. Today you learned why the moon has phases.
So that gives us more information about the moon and the phases the moon goes through and the cycle it makes. So let's go back to our lecture slides. So we just find the correct slide quickly. It's this slide. Quick question. I want to know, why does the moon appear red when it sets in the morning? So may you please explain the Earthshine concept? Okay, so let me do these two questions first. So the first one is, why does the moon appear red when it sets in the morning? So there should be a whiteboard function. So let's stop sharing the slide. Here we have the whiteboard. So the moon will always appear more redder when it's setting and when it's rising. And the reason for that is, let's say draw this as Earth, and let's make the moon green. So if we are located on Earth, so let's say for this example, we are sitting right here in the Northern Hemisphere. So right here, looking towards the moon, we have a lot more atmosphere to look through. So let's make the atmosphere purple. So right here, we have a lot more atmosphere. But when the moon goes on through, let's say a couple of hours later, when it is directly above us, and we are now looking towards, wrong color, we're now looking towards the moon, there is less atmosphere we are looking through. So one of the things that our atmosphere actually does, it scatters blue light. So have you guys ever wondered, let me ask you this question for the class, why is the sky blue during daytime? Any ideas? The reason why the sky is blue, I've found that's also a question I like to ask during these semesters and exams, is not because of our oceans or anything like that. So it has to do with the type of molecules and how they interact with light. I think almost, but the main reason is it's called the Rayleigh scattering principle. So the physics students will learn a lot more about the Rayleigh scattering principles. But what is in fact happening. If you look at a prism and you shine white light through a prism, that light is split into these 7 primary colors, the colors of the rainbow. So what happens with that is when the light goes through the atmosphere, the blue and purple colors of the rainbow is scattered across the atmosphere due to the Rayleigh scattering principle, and your reddish yellow coloring continues straight to the ground. So due to that, the sky is blue and the sun appears as yellowish, bluish. And the bigger the atmosphere is, the bigger that scattering principle is. So when the moon is rising or on this side setting, we have more atmosphere looking through. That means more scattering is happening, and that is why the sun, not the sun, the moon appears more red when it's rising or when it's setting. But when it's overhead, it looks more normal. So how about the blue shift and red shift? The blue and red shift has nothing to do with the color of the atmosphere, but we are going to learn a blue shift and red shift later on. That has to do with the expanding of the universe and how other objects in the universe moves. So another concept, what you ask is, hello sir, may you explain the earth shine concept? So with earth shine is, when it is full moon outside and you have no other lights, let me ask you this, can you still see in the moonlight? Yes, that's exactly it, because the sun shines on the moon and the moon reflects light onto Earth. Earth shine is exactly the same principle. The sun shines on Earth, and then Earth reflects that light back onto the moon. So that is why when it is new moon, when the moon is supposed to be completely dark, you can still make out the moon and see it a little bit. And that is Earth shine. It's literally the part of Earth that's now in the sunlight, reflecting light onto the moon. Does that answer your question? Awesome. So let's go back to the slides. Yeah, we just find the correct slide. So when we are looking at the Earth-Moon system as a whole, the moon is measured about 0.5 degrees in diameter, and it moves roughly 13 degrees in 24 hours, so more or less 0.5 degrees per hour. So in your moon observation, you will actually see this happening. Something interesting, when we look at the angular diameter, that means when we measure the diameter of the moon, it is roughly 0.5 degrees when we angular diameter. But the angular diameter of the sun is also 0.5 degrees. So that is why we get solar eclipses that we will talk about in a bit. So here we can see as the moon orbits around the sun, we can see the different phases as the part that is lit up. So here we can see all the phases. So here we can see from new moon all the way to full moon, and from full moon all the way back to new moon. So here we can see a diagram of how it works. So new moon is where we start. So the moon is directly between the Earth and the sun. So the far side of the moon is illuminated and the side facing Earth is not. So here we have the fact waxing crescent. Here we have first quarter, waxing gibbons, full moon, waning gibbons, third quarter, and then the waning crescent again. And that cycles is about 29 days for it to repeat. So now, lunar eclipses. Who of you have seen a lunar eclipse? Awesome. So I can see, okay, cool. A lot of you have. So lunar eclipse is something that, it's not that something special. So the media usually make a lunar eclipse as a very special event. Yes, it's beautiful to watch, but depending where you are on Earth, a couple of lunar eclipses happens per year. At minimum, there's about 4 lunar eclipses per year that you can see across the globe. Every year, doesn't matter where you are on Earth, you can see a partial lunar eclipse all the way up to a full lunar eclipse. And that is just due to the reason that and the new moon, during the new moon phase, not a new moon phase, when we have the full moon phase, the Earth's shadow, so we have the sunlight coming in from this, and the moon moves through the Earth's shadow. So we can always see it. So before going on, I want to show you one last video for
Present. Present. We humans apply a great coincidence. It's a coincidence of time and of space and of math. The coincidence is this: the sun is about 400 times wider than the moon, and it's also, on average, about 400 times farther away than the moon. The apparent size of an object in the sky depends on how big it is and how far away it is. So these numbers being equal means the sun and the moon appear to be about the same size as the sky. And that's where another interesting thing comes in. Sometimes the moon passes directly between the Earth and the sun. It doesn't happen all that often, but when it does, you get magic. Or even better, you get science. You get an eclipse.
One giant leap for mankind.
An eclipse is a generic term in astronomy for when one object passes into the shadow of another object, darkening or blocking it. A solar eclipse is when the moon blocks the sun, casting a shadow on the Earth. And a lunar eclipse is when the Earth blocks the sun, casting a shadow on the moon. But how do they work? Well, the moon orbits the Earth once per month, and the Earth orbits the sun once per year. If the moon's orbit were perfectly aligned with the Earth's, essentially sharing the same plane, we get a solar eclipse every new moon and a lunar eclipse every full moon. But we don't. That's because the moon's orbit is tilted with respect to the Earth's by about 5 degrees. What that means is that at new moon, the moon can be as much as 5 degrees away from the sun, passing above or below the sun in the sky, thereby missing it from our perspective. But sometimes the moon is in the right place at the right time, and at new moon, it lies perfectly in line between the sun and the Earth. And when that happens, we get a solar eclipse. This geometry happens at least twice per year, and sometimes as much as 5 times per year. What's happening physically in space is that the moon is casting a long shadow. Usually that shadow misses the Earth, but during an eclipse, the moon's shadow falls on the Earth's surface. In fact, there are 2 shadows from the moon, one inside the other. One is a narrow cone tapering to a point away from the moon. If you were anywhere physically inside this cone, the moon appears big enough to completely block the sun. That means the shadow is very dark, and we call it the umbra, which is Latin for, you guessed it, shadow. Outside of this deep umbral shadow is a wider conical region where, if you're in it, the sun is only partially blocked. You can still see some of the sun past the moon. You're getting less light, and so you're technically shadowed, but it's not quite as dark as the umbra. This region is called the penumbra, pen in this case for Latin meaning almost or nearly. When the umbra touches the Earth, we get a total solar eclipse. But what does that look like from the ground? You don't get a total solar eclipse right away. First, the edge of the moon slips in front of the sun, and we see a little dip in the sun's limb, its edge as seen from the Earth. That's the start of the penumbra sweeping over you. As the moon slowly moves, that dip grows, becoming a bite. The sun becomes a thick crescent, then a thin one. As the sun becomes an ever thinner crescent, the sky begins to darken. Then, finally, the moon's black disk completely covers the sun. The umbra sweeps over your location, and at that moment, totality begins. You might think that this just means the sky gets dark and it's like night outside for a while. But a total eclipse is far more than that, and that's because of the sun's corona. As I'll cover in more detail in a future episode, the corona is the sun's atmosphere, an ethereally thin envelope of gas that stretches from the sun's surface into space for millions of kilometers. It's really faint and therefore usually completely overwhelmed by the intensely bright light from the sun. But when the moon blocks the sun's face, the corona becomes visible. It surrounds the sun, filaments and tendrils extending into the sky, an incredibly beautiful sight. I know many people who have said it's the most spectacular thing they have ever seen. And there's more. The moon's edge isn't smooth. There are craters and other depressions. Craters right at the moon's edge allow sunlight to stream past. We see these as bright patches around the eclipsed sun, which are called Baily's beads, because they were first described by English astronomer Francis Baily in 1836. Because the moon and sun are very nearly the same apparent size, totality is brief. The longest it can last is only about 7 or 8 minutes. That's how long it takes the umbra to move over one spot on the Earth. When totality ends and the moon starts to move off of the sun's face, for a moment, just a single spot of the sun is unblocked, glowing fiercely on one side of the moon. Sometimes you can get a circle of light around the moon's surface, and together with the bright spot, it looks like a celestial wedding ring. In fact, this is called the diamond ring effect. Then, inexorably, the moon pulls away from the sun, and the order of events is reversed. The umbra is gone, but you're still in the penumbral shadow. The sun shows a thin crescent, then a thick one, then a dip in its side, and then it's all over. The umbral shadow of the moon is pretty small where it hits the Earth, so a total eclipse is a local event. If you're too far north and south, you don't get a total eclipse, you only get a partial one, which is still cool, but lacks the mystique of a total eclipse. Remember too that the moon's orbit around the Earth is an ellipse. That means sometimes it's closer to the Earth and sometimes farther. If a solar eclipse happens when the moon is at the far end of its orbit, it can actually be smaller than the sun in the sky. It doesn't block the entire face of the sun, and it leaves a ring of light around the black circle of the moon. The technical name for this shape is annulus, so this event is called an annular eclipse. A lot of people think if you look at a total solar eclipse, you can go permanently and completely blind. That's really not true, but some parts of eclipse watching are more dangerous than others. I mean, obviously, it's not a good idea to stand there and stare at the sun. Looking at even the uneclipsed sun for more than a moment is painful. And that pain is the result of the damage that solar radiation is doing to your retinas. So I don't recommend it. Duh. But when viewing an eclipse, the real concern is right after totality ends. During totality, it's dark, so your pupils have dilated to let more light in. But then there's the flash of sunlight when the moon moves off, and that's intense enough to damage your retinas. That's why astronomers recommend extreme caution when viewing an eclipse, because that flash can catch you by surprise. When viewing the sun, don't just stand there and stare at it. You should always have eye protection. And make sure you have safety-approved filters. Don't try the homemade tricks you might have heard of, like looking through an old CD or DVD or using old-style camera film as a filter. These can let through too much infrared and ultraviolet light, and again can dilate your pupils, actually making things worse. Lots of companies make inexpensive filters that are great for sunspotting. We have links in the doobly-doo for more information on eye safety. Now, you don't have to worry about hurting your eyes at all when viewing a lunar eclipse, because in that case, it's the Earth that blocks the sun, and the Earth's shadow falls on the moon. So go nuts. But one big difference between the two kinds of eclipses is who can see them. A solar eclipse is localized to one spot on the Earth, or really a swath along the ground as the moon's umbral shadow sweeps across the Earth's surface. But a lunar eclipse is when the moon moves into Earth's shadow. So anyone on Earth facing the moon can see a lunar eclipse. This is why I've seen dozens of lunar eclipses, but never a total solar one. I've never been at the right place at the right time. Not that I'm bitter. The Earth has umbral and penumbral shadows too. When the moon first enters the Earth's penumbra, the dimming is so slight you hardly notice it. But as the moon moves deeper into the penumbra, it starts to darken. Sometimes it changes color, turning a deep orange or blood red. That's because the Earth is starting to block the sunlight heading toward the moon, and the only light that gets through is coming through the thickest part of our atmosphere. This blocks blue and green light, leaving only red to come through. That's why the moon and sun look red to us when they're on the horizon, rising and setting too. When you look upon the red eclipsed moon, you're seeing the light from all the sunrises and sunsets in the world hitting the moon and reflecting back to us. Finally, the moon starts to enter the Earth's umbra, and the real eclipse begins. At first, it looks like a bite is taken out of it. That curving arc is the shadow of the edge of the Earth. The moon moves deeper and deeper into the shadow until it's completely darkened. The Earth is bigger than the moon, so the Earth's umbra is much wider. While a solar eclipse is over in minutes, a total lunar eclipse can last nearly 2 hours. I once saw a lunar eclipse so deep that it took me a minute to find the moon in the sky. There's not a lot of new science you can do with a lunar eclipse, but if you know a little geometry, you can use the size and shape of the Earth's shadow on the moon to get the relative sizes of the Earth and moon. Ancient Greeks did just this and got a number that wasn't too far off. They also knew how big the Earth was using other methods, and so they had a decent estimate for the size of the moon nearly 2,000 years before the invention of the telescope. They also knew the shape of the Earth's shadow was always a circle, which only makes sense if the Earth were a sphere. If the Earth were flat, it would sometimes cast a thin shadow, but it never does. Pretty clever, those ancient Greeks. One final note. Because of tides from the Earth, which we'll learn more about in detail in a later episode, the moon is slowly moving away from the Earth by about 4 centimeters a year. As it recedes, it's slowly getting smaller in the sky. This means that eventually it will be too far away to completely cover the sun, and we won't get any more total eclipses. Doing the rough math, that will be in about 1 billion years. Better watch eclipses while you can. Today you learned that a solar eclipse is
So hopefully that helps explain it a little bit better, and it's also very cool to observe. So let me go to our slides, then I'll answer the questions. Let me just find the correct slide. This is the correct slide. So one question is, why is it that Earth has 1 moon while Jupiter has 4? So one thing is Jupiter has 4 big moons that we can see easily through binoculars and a small telescope. But the last time I checked, Jupiter had about 84 moons. Saturn also have a lot of moons. We're going to do an entire lecture just on moons as well. But when the sun was formed, or were busy forming, the planets was forming at exact same time the sun was forming. And while that was forming, the different moons in our solar system were also forming the exact same time as the planets and the sun was forming. So with Earth as 1 moon, there was enough material around Earth for it to form 1 moon. And if you go outwards in a solar system, Jupiter had enough material to form big 4 moons and a lot of smaller moons, but we will talk about that in a later lecture as well. Another question. Does the moon rotate so slowly its other side, or do we only see the same side of the moon? We only see the same side of the moon, and that is because we say the Earth is tidally locked to Earth. So that means while the same speed the moon rotates around its own axis is also the exact same speed as it rotates around the Earth. So that is why we only see the same side facing Earth. So if the moon cycle is 28 days long, why are months 31 days long? So the moon cycle is roughly 29.5 days. So a month is based on that, but due to changes being made by the different calendars, months usually has 30 and 31 days, and that's why February has 28 days. So the exact length of a month is not direct science. It's based on the lunar cycle, but how to fit everything in is chopped and changed a little bit over time. So another question, considering the moon is moving away from Earth, does that mean solar eclipses in the far past would also cover the corona of the sun? Yes, that is also true. So in the far past, it would have covered the corona as well. Yes, you are completely correct. So this is just an illustration of how it works. If this is the sun, And here we have the Earth. Then the Earth casts a shadow. So this deep shadow is the umbra, and this light shadow is the penumbra. So here we can see it casting. So when the moon moves in a penumbra, you don't really notice it. But when it moves into the umbra, we can clearly see it. So this is how our lunar eclipse will look like, our full lunar eclipse, depending on where we are. So the moon moves through the umbra and is completely covered. In about 2 hours' time, it will move outside the other side and the eclipse will be done. So these are some images of a partial lunar eclipse, which is very cool to see. So for interesting sake, let me quickly see when the next lunar eclipse in SA will be. Okay, cool. So on September 7th, I did quickly did a search, we will have a full lunar eclipse in South Africa this year, which will be very, very cool. Then on the 14th of March, we will have in South Africa. So that is not usually spectacular to see because the moon is only visible through the penumbra, so you won't really see anything. But on September 7th, we will have a very, very cool eclipse. So yes, that will be spectacular later this year to see. So we also in the video learned about solar eclipses, when the moon covers a shadow. So we both say both is about 0.5 angular of 0.5 degrees. But that is because the sun is about 400 times larger than our moon. But an average is also 400 times further away. And that is why we can cover it. And that's why we can see a full solar eclipse and in some cases partial lunar eclipses. So here is another reasoning with numbers, and this is also a question I can perhaps ask in the semester test or exam. And for your moon assignment, this is one of the methods you can use to calculate the diameter of the moon. So this example is very important, but let's go through it. So figure 3.7 shows the relationship between the linear diameter, angular diameter, and distance of an object. In this case, the moon. The linear diameter is simply the distance between an object's opposite sides. So you are referring to linear diameter when you're ordering a 16-inch pizza. The pizza is 16 inches across. So the average linear diameter of the moon is roughly 3,470 kilometers. The angular diameter of the object is the angle formed by lines extending towards you from opposite edges of the moon, meaning at your eye. Clearly, the further away a given object is, the smaller the angular diameter is. To find the angular diameter of the moon, you need to use the small angle formula. It shows you to calculate the angular diameter of any object, which is a pizza or the moon. This formula is very important in astronomy, and you will encounter it in uses many times in later chapters. So with this equation, on the left-hand side, let's see if I can make the point a little bit smaller. So on this side, on top, we have the angular diameter in arc seconds. Below, we have the constant of 2.06 times 10 to the power 5. Here we have the linear diameter, and here we have the distance. So this right here is the linear diameter. This is the angular diameter. This is the distance. So for your moon assignment, you know what the distance from Earth to the moon is. You can measure the angular diameter from your observations. And then you can create and solve for the linear diameter. So this is one of the methods you can use. So in the small angular formula, you must always use the same units for distance and linear diameters. The version of the formula shown here has arc seconds as the unit of angular diameter. You can use this formula to find any one of the three quantities involved, the linear diameter, angular diameter, distance, if you know the other two by cross multiplying. So example, the moon's linear diameter, so that means this diameter over here, let's get me a different color, this diameter over here is 3,470 kilometers, and its average distance from Earth is 384,000 kilometers, so this distance over here. So what is the angular diameter? So easy to do, you have those two others, we plug it in, so we have this one, we have this one, we have this one, we plug it in, and we can calculate it as 31 arc minutes or about 0.5 arc degrees. So where does that constant here comes from? That constant, the number 2.06 times 10 to the power 5 in the formula, converts the angle units from radians to arc seconds, and that is the only thing it does. So it's straightforward plug and play math. So for the moon assignment, this is one of about 4 methods you can use to calculate the linear diameter. I can see someone writing, please don't write on my slides because everyone else can see it as well. So I want to clear the annotations. So for the moon assignment, while doing the observations, where is my pen? You need to calculate the linear diameter. So you are going to observe the moon every day for 10 consecutive days. So from your observations, you will determine the angular diameter. Once you locate the angular diameter from your observations, we know what the distance from the Earth to the moon is. Then you have these two quantities and you can just solve for the linear diameter. So read up about this method, figure out how you are going to implement it with your observations. So when looking at this system, when we have a solar eclipse, the sun moves, the moon moves between the sun and the Earth. And here where this dot is, that is the total solar eclipse when we are in the penumbra. So when you are in the penumbra, we will have a partial solar eclipse. So again, here we can see in the dark area, let me get the pen out. So when this will be a full solar eclipse, so in this area right here, we will have a total eclipse. And when we are in the penumbra, so in this area over here, and this area over here, we will have a partial solar eclipse. So this is a cool image that was taken in the US last year when they had a full solar eclipse, which is actually very cool and very well done. So today I'm going to leave you off with this quote. Everyone you will ever meet knows something you don't know. And that, ladies and gentlemen, is today's lecture. Do you have any questions? If you have no further questions, you're more welcome to log off. Then I will see you next week, Monday, in person in class. So, question. Yes, sir, I have a question from last lecture. You are more welcome to ask your question. You can type it or you can unmute yourself and ask it, whatever you're comfortable with. And so what was the app you used to check if the moon is above the horizon? So I literally just did a search. I will post a link right now. So if you just go to Google and you say moon rise and set times, it will be the first hit on Google. So let me quickly paste the link for you guys. So it is this link over here. So will the lecture be recorded and posted? Yes. I will upload it within the next 30 minutes. Sir, can we take pictures of the moon and draw it later? Yes, you can do that as well. You can draw pictures, you can draw it. As long as I can see on your diagram the position of the moon shifting every day and that a phase is also changing. So what's your YouTube channel? I will send a link or post a link to my YouTube channel while I upload this in the next half an hour. Then I will also provide you a link with the videos I made during the COVID years and also for today's lecture.
Sorry, sir, can you hear me?
Yes, I can hear you.
Okay, cool. So, yeah, I've got a question from last lecture. I'm gonna try to explain it. But
Okay.
it involves where if two stars differ by 5 magnitudes, then they've got a flux ratio of 100.
Yes. So let me go back to that slide. Let's see if there's a faster way I can navigate to it. Yes.
Okay,
So
so
it's this slide.
the screen is still gray currently.
Okay, it should.
But
Let's give it a second. It should load on your side momentarily.
okay.
So one thing that we have done with this is if we have two different stars and they differ with the magnitude differs by 5, that will give you exactly a ratio of 100. So when you have the flux of star A and the flux of star B, that will give you a ratio of 100. So that is something astronomers has defined. So when you want to find it for exactly one scale in magnitude, you can take 100th root of 100, and that gives you 2.51. So now we have a standardized definition that every level of magnitude you have 2.51 in between.
Okay, so that does pretty much make sense to me, but I was just wondering, like, with with finding between two stars that differ by 1 magnitude, the flux difference,
Yes.
the way you like fifth root it, I was wondering if there was a way to prove that mathematically, because it makes sense, but I just wanted like a sort of a more foundational.
Yes, there will be. So I will actually find out for you if there's a proof. So there should be a proof for it. So this is just a straightforward explanation, but I will find a proof and I will show it to you next week, Monday's class, if that is fine with you.
That is perfect. Thank you, sir.
It's a pleasure. So a question, sir, I know you will probably explain this as the semester continues, but in assessment it says we must graph the moon's changes. What is exactly meant by this? Must we draw the moon's changes, graph the images we take or something? So what's happening with that is what I mean. Let me get the whiteboard out again. Let me clear this. So let's say you make your observations every night. So let's do this. So let's say, okay, in observations, here is, for example, a building. Here is a tree, for example. Over here is a car park. Say, for example, let's draw lines for the car park. Then you must observe the moon for 10 consecutive days. So let's say on day number 1, the moon is over here and it's a new moon, meaning you won't see anything, for example. The following day, the moon will be over here, and you'll see a little bit. The following day, it will be something like this. The following day, it will be something like this. Following day, like this. Following day, like this. And that is the drawing I want to see, or from your observations, how the moon's position differs every day when you observe it from the exact same time and same position every day, how the position in the sky differs, and also how its phase differs. So must we draw the moon's changes, graph the images, or take something else? So that's up to you. You can draw it, you can take pictures. If you take pictures, I still want to see your sketch. That means you have to take every day's picture and put it on the. Doesn't matter what you want to do. You can draw it, you can sketch it, you can paint it, whatever you want to do, as long as I can see your observations. So another question. Sir, you simply must ensure that the moon is over the horizon on the first day and the 10th day of the observation. Yes. So it doesn't help if, say, for example, you can't get to 10 observations. Remember, the moon's position will differ every day by about 13 degrees. So that is roughly 15 minutes every time. So it doesn't help you get to day number 4. Now all of a sudden the moon disappears below the horizon. So make sure you can see the moon for those 10 observations. Then last question. So would it be best to have landmarks like buildings, trees, etc., not just pictures of the sky? So that depends on the method you're going to use. So if you are going to use the small angle approximation method, yes, then it will help if you have landmarks as I've drawn here. But if you're going to use another method, there's no need for landmarks. Then I just need this part over here. Do the objects in the background, example buildings, trees, have to be drawn neatly? No, it doesn't have to be drawn neatly. It is just a reference for your method you are going to use. It's a pleasure. So if there's no further questions, you are more than welcome to log off. Then I will see you all next week, Monday, in class. Have a wonderful day and good luck with the rest of the week.